All right, let's try another video solution here. How about from chapter 12, number 22 here. And it says a yellow object is lowered carefully into a completely full beak of water where it floats. All right, so to help with my thinking, I'm going to draw a picture here. Here'll be my beaker, and the beaker is filled right to the top, okay, Lord, and it floats. So what's going to happen is this object, which they say is yellow. I'm not so sure that that's important, but maybe it'll keep track of another object coming up. But this yellow object then, because it floats, will not be completely underwater or under whatever the fluid is. Let's see, a yellow full. It is water, beaker of water, and it floats. Okay, so it's displaced this volume, not. And I just want to make it very clear then, the volume it displaces is not the whole volume of the object. See, the object is floating. Okay, now that fluid that is displaced flows over and out the beaker. So maybe we catch it here. And it says it causes 28 cubic centimeters of water to spill out. So we measure it in some kind of beaker down here or graduated cylinder, and we get 28 cubic centimeters. Now, remembering that the density of water is 1 gram for every cubic centimeter. If we have 28 cubic centimeters, then we also have 28 grams that spill out. I don't know if that's going to be important, but I'm going to keep that in mind here. That okay, so this volume and this mass of water has spilled out, and so the amount that is submerged is this volume. Okay. Now, it says the same object is then lowered carefully into a completely full beaker of gasoline. All right, so maybe I'll make a little dividing line here and say, okay, second experiment. So here is our beaker, again filled all the way to the top. This time we put in the object, and it doesn't float, it goes completely under. Now this would tell me more volume would flow out, because clearly only part of the volume of the object was this 28 cubic centimeters. So now this is going to be more than 28. It's going to be the whole object. Okay. Because there's 28 cubic centimeters of water to spill. Let's see, the object is then lowered carefully into a completely full beaker of gasoline. They give you the density, where it sinks, causing 40 cubic centimeters of gasoline. Yeah, see, that makes sense. So it's got to be more than 28. In fact, it is 40. Okay. To spill out. In which liquid does the yellow object experience the greater buoyant force? Well, we could quickly answer this without doing a calculation, and I think I will, but I won't stop there because I don't think the author wants you. This is in the exercise, so I think he wants a calculation here. But we know this, that when this one was floating, if I did a free body diagram, it would be pulled down by the weight of the yellow object, so mg, and I'll put a y here, meaning the mass of the object, the yellow object, and it's being pushed up by the buoyant force. And since it's floating, those are the only two forces, and so if you add up all the forces and set it equal to ma, it's got to be 0. So that is telling you that the buoyant force is equal to the weight of the object. This is similar to that problem we did with the I forget which number it was, but it had a 50-ton ship in freshwater and saltwater, and was asking which one would it displace more. Oh, there it is, number 45. But anyways, so anything that's floating, we know the buoyant force equals the weight of it. Because if either one of those is bigger, it moves up and down until those either balance or it goes all the way to the bottom. And that's what's happening here. So what's happening here is if you do a free body diagram, you'll have of course, the weight, mg, and I'll put a little y. You'll have the buoyant force. But clearly, the fact that it sunk tells me that the buoyant force was not enough to overcome the weight, and so the buoyant force was less than the weight, which is why now when it sits on the bottom, there would be another push with a normal force. And so now it settles out. And so the sum of the forces equaling ma, and that has to be 0, would tell me that the buoyant force plus this normal sitting on the ground minus the mg has to be 0. And so that would clearly mean that the buoyant force would be mg minus whatever that normal force is. And now I don't know what it is, but I know it's got some number. And so back here, the fact that we need a normal force tells me right away that the buoyant force in the gasoline is less than the weight. And remember, over here in the water, the buoyant force was equal to the weight. So I would draw the conclusion right away that the buoyant force when it's in the water must be greater than the buoyant force when it is in the gasoline. Which answers the question, really. However, I think they want us to go a step further, so I will, because it's on the exercise. And let's actually get a number. Let's calculate what the buoyant force is in the water and what it is in the gasoline, and you will hopefully see that the water is greater than the gasoline. So with that in mind, let me just do the buoyant force. Let me do the water. Let me do that phrase again. It's Archimedes' principle. The buoyant force is equal to the weight of the displaced fluid. So you calculate weight with mg. Maybe I'll put a little W here for water, because we do have to be careful in this problem, because as we talk about water, or we talk about weight, there's really 3 weights going on here. There's the weight of the yellow object, which doesn't change, but then there's the weight of the water that flowed out, and then there is also the weight of the gasoline that flowed out. Now, I guess there's also the weight of the gasoline. It's still left in the beaker, and the weight of the water is still left in the beaker. Or, for that matter, the weight of the water before we put it in, or the weight of the gasoline before. So there's a lot of weight. Or we could even say, what's the weight of the beaker here? But there's just 3 of them that are needed for this problem that can confuse you. And so my warning for any of these Archimedes one is remember that Archimedes says that the buoyant force is equal to the weight of the fluid displaced. So it's not equal to the weight of the object. It's not equal to the weight of the beaker holding the fluid. It's not even equal to the weight of all the fluid itself. It's equal to the weight of the fluid displaced. So keeping those words in mind and remembering that weight is always calculated as mg, I'm just going to put a little w underneath it to tell myself that I'm talking about the mass that overflowed. Now remember earlier we said that that was 28 grams. So I'll go ahead and put in the 28 grams, although maybe I will convert it to kilograms, and I'll use G, just kind of a rounded 10 to make my math a little bit easier. And so 10 times this makes 0.28 newtons. So there would be the buoyant force of the the buoyant force on the yellow object coming from the water, because it's equal to the weight has been displaced, and what has been displaced is equivalent to that volume, which is how we got that. All right, so same logic here. Let's do the buoyant force for the gasoline. So it is completely submerged in the gasoline over here, and it is being pushed up by the buoyant force. And I'll say it again, the buoyant force is equal to the weight of the fluid displaced. So in this case, it is gasoline. So when I put mg, maybe I'll put a little g underneath it for gasoline, and say, all right, then let's calculate the weight of the gasoline that has been displaced. Now, to do that, we'll need to know the mass. And we did not calculate the mass displaced. We only left it at the volume. This we did just because it was so easy because it was a 1. But we really have to do the same kind of calculation. So let me put here density equals to mass over volume. The density was 0.68 grams per cubic centimeter. The mass is what I'd like to find, and the volume is the 40 cubic centimeters. And that means that the mass of the gasoline that flowed over the side, 0.68 times 40, is 27.2 grams. Okay, so this is the mass of the gasoline that flowed out. And I'll come back over to here. The buoyant force is equal to the weight of the displaced gasoline. And the displaced gasoline is equal to the weight that flowed over. So putting in a mass of 27.2 grams, although I'll convert it to kilograms, and multiply it by G, which is roughly a 10, I will get a 0.272 newtons of force from the buoyancy of the gasoline. And clearly that is a smaller number, not by much, but the gasoline, as we said earlier, gives a buoyant force that is smaller than the water. Okay? So remember, buoyant force is equal to the weight of the displaced, not the volume displaced. And I think that's why this makes it a good problem, because it might even sound confusing that, wait a minute, the whole thing went under. Well, the whole thing went under because even though it displaced at a lot more volume than that, it was never enough to equal the weight of the object. So obviously the weight of the object is the 28 grams. So just almost. It almost was enough to float the object in gasoline, but it was just a hair under. All right, hope that one helps.